Yes, perfect.
Brilliant. Excellent. Right, I'm going to turn my camera off just so this is a bit as smooth as possible. So yes, welcome to this session on decarbonising and sustaining track. I currently sit within the supply chain operations and route services. Previously, I was in the technical authority with Network Rail. Most of this work stemmed from the technical authority and was sort of passed over. So it's a joint effort between technical authority and supply chain operations, and it's something that we've been sharing with the PWI. So this is it's ongoing work. It gets updated every time I do this new slide deck. So this was previously presented in September, and there's quite a few other presentations for this. So we're always getting new material. So let me just take you first through what we mean by, I guess, carbon emissions and how that applies to Network Rail. So within Network Rail, we have three scopes for carbon emissions. Scope 1 is the direct emissions. That comes from our sort of company facilities and from our vehicles. As you can see, it's a very small percent, only 1%. Scope 2 is from the indirect emissions. So that's the actual energy that we purchase to operate our business, and that's 2%. And scope 3, which is the largest, obviously, 97%. That's 7.8 million tons of CO2. And that's the indirect carbon from capital goods purchased and anything also within the infrastructure, which is embodied. So a lot of what I'm going to talk about today is about that embodied carbon within the track, which forms part of scope 3. And just to give you a flavour, the track infrastructure plays around a quarter of that 97%. We've got some exact figures, but it changes by the day. But and all this data does obviously need to be verified as we get new data. But a large chunk of scope 3 is within the track. Why is it important? Well, the Department for Transport introduced a requirement for Network Rail, and our CEO, Andrew Haynes, actually bought into committing for Network Rail to deliver whole life carbon assessment and reporting for all capital projects. So those projects funded over 500 million were back in February, and we're now at a stage where all our major projects are reporting on carbon. Whole life carbon covers all the infrastructure life cycle stages, so it's construction, operation, maintenance, and also the deconstruction and removal. These life cycle stages are all described within BS 17472 and also within PAS 2080. So that helps us calculate how much carbon we actually embody or generate from sort of cradle to gate. There are science-based targets to these as well. So we're trying to create science-based targets for a lot of our materials, and we're now setting those targets within Network Rail with our suppliers as well. There is a standard, so there's a level 2 business process that was issued 2 years ago, which basically states that we should be looking at carbon and calculating carbon, and also whole life carbon as well. So that's a standard that is a business process that all projects should be following. And just for the avoidance of doubt, so what do we mean by kilograms CO2e? So it's the equivalent carbon dioxide kilograms. And it's an actual unit we use. It's not necessarily just carbon dioxide, it's all the other greenhouse gases as well, such as nitrogen and so on. So it's not just CO2. And it's become I guess, the metric we're using for carbon at the moment. These are the life cycle modules that we use to assess carbon within our materials or within projects. So A0 to A5 is really the before use, so preliminary studies, concepts, then we get into the actual manufacturing, that's the cradle to gate. The gate is when it gets transported to site, and then we have the installation A5, which is construction installation. So in terms of track renewal, A5 is the track renewal part, A0 to A4 is the materials being sourced and manufactured. B stage is the U stage. That's when we operate and maintain the track. We may refurbish it. We may do other things to it to keep it going until C, which is end of life removal. As you know, with track, we actually remove and then install in the same phase. So those two phases are joined together. There is also a beyond life cycle D. So that's if we're actually recycling, repurposing, or reusing materials for other uses. So we don't tend to use that just yet, because we're still trying to find out those calculations. There are some sleepers we know that we can use in that category and start to calculate, but until we get some sort of defined data for that, we've excluded that for now. So we talk about science-based targets. This is something that we're working with all of our suppliers. So these are carbon reduction targets set by our companies. They're science-based, and they are science-based if they align to the 2015 Paris Climate Agreement. So there's certain criteria there to meet. And that goal really was the temperature increase from pre-industrial times below 2 degrees, and look at ways to limit it to 1.5 degrees. That's what we're basing it on. And these are now becoming sort of the credible approach to achieving net zero by using these science-based targets. And Network Rail are one of the first railway organisations in the world to set these science-based targets, and they are quite ambitious, and to help again that 1.5 degree global warming. So that's part of obviously our climate strategy and the net zero strategy that the environmental team has now put into place. 75% is the goal for our suppliers to meet the science-based targets. We've actually got more than that within track. I'd say around 80%. So all of our sleeper suppliers, our rail suppliers, our ballast suppliers are all actually providing us with their data, and we're setting targets that we know align with science-based targets as well. So I think in the track environment, we're in quite a good space, and we can now actually start to set those targets. So looking into track renewals and the CO2 in track renewals, some of you may be aware of the RSSB carbon tool. So we use this as a sort of 2021-22 track renewals baseline, and that's where we were able to look at how much or what percentage each material type adds to this. So 41% is rail, and that's including sort of the welding and the stressing. So that's all installation, rail, welding, stressing. Then concrete sleepers, then locomotives, and then ballast, and then we start to run down to fastenings, workforce, and tamper, and so on. So the top two materials really are rail and concrete. So concrete sleepers. In terms of rail, we've been looking at how we can reduce the carbon in our current arc furnace rail to using electric arc furnace rail. So that can reduce from 2.2 kilograms per kilo, so it's quite a high percentage for rail, down to 0.8. So that's quite a large reduction if we start to use green steel, which is electrically arc furnace steel, and it uses recycled steel as well, at a higher percentage. We could use longer lasting rail, wear resistant grades as well, so that could last longer. So we can look at sort of a life cycle reduction of carbon. We could monitor wear more precisely with using laser profiling and rail profiling data more accurately, rather than using older sort of methodologies, and improve the serviceability and circularity for cascading. So there are other things we can do to improve that. With sleepers, we do have low carbon CEM2 mixes that reduce the carbon from 100 to 60, and you'll see some data on that later. There's also other things under sleeper pads to increase the life, reduce the ballast and track system degradation, and also that reduces the whole life carbon and cost as well. So there's savings there, and possibly using recycled rail pads and insulators. Locomotives, not part of this study, but we're looking at biofuels and looking at rechargeable and EV vehicles as well, and for staff to site and so on. So it's another area that's being looked into. Just to contextualize and break down the track into what people may, I guess, realise is, so within 400 metres of track construction, the rail actually equates to 204,000 miles driven by an average person. Concrete sleepers, that's 10 homes electricity demand for a year. and locomotives over 4 million smartphones charged. So it just gives you an idea of where that comes from. One of the initiatives within the TA that's introduced in March 21 was composite sleepers. This is approved under trial acceptance as a replacement for timber sleepers that contains 1/3 of the CO2 compared to a G44. So full PA is actually now in place, and we're looking at full PA for higher speeds as well. At the moment, they're approved up to 100 miles an hour for Cat 1 track. And there's two various depths of them as well, 135 mil and 155 mil. Ideal for use in tunnels as well, where you've got smaller and more confined spaces where you need to short end and chamfer, and also on structures where you need a lighter sleeper because they're a similar weight to timber, 1/3 of the weight of concrete. So the composite sleepers do deliver a circular economy. They're manufactured from recycled UK waste. So looking at this this loop diagram on the right hand side, starting off with the bottles there on the bottom, going into the UK waste stream, and then coming around into turned into pellets, and then molded, heated and molded into the sleepers. Then installed for a 50-year life, and then they can also be repurposed and reused or cascaded or recycled. So the full loop cycle is used there. Whereas with a plastic bottle, you're only looking at something like sort of 6 months from start to finish once it's in the cycle, or in some cases 6 weeks. And then after a sort of 6 cycles, it starts to deteriorate as well. So this is a lot larger loop, which means we get carbon sort of locked in and embedded in for a lot longer time. We've done some work analysing the difference between composite sleepers and concrete sleepers in track renewals and how much saving we can offer. So if you look on the left-hand side where we've got the embodied CO2 for using concrete sleepers, using composite sleepers, and then compared to the G44 there. So we're saving, I think, 100 tons of CO2, which is 17% by just changing the sleepers only. So it's quite a large amount. Other work we're doing to look at sustainable sleepers and greener sleepers is a technology for, on the left-hand side, that's a sleeper that uses serviceable sleepers and then coats them in plastic. There's even a solar panel on there as well to add some extra benefit. We found that technology not to be so good because the recycled rubber does actually erode and does introduce plastic into the ballast, so that's not a good idea. In the centre there is a sulphur sleeper, so this has been decided to be taken on, and colleague in TA is actually trialling the sleepers in the next 6 months, and that uses sulphur in place of cement in the mix, and it's fully recyclable as well. So you can heat the sleeper up and basically remold the sleeper using the same materials, so fully recyclable and circular. The right hand side is another plastic sleeper, uses less plastic, but as you can see, its shape beds into the ballast, so it provides sort of increased lateral resistance, and works better with the ballast as well, and reduces the sort of ballast degradation. So a lot of this is being assessed through the whole life cycle and various other different performance criteria that we've developed to make sure we get the right sleeper, rather than just saying this is a G44, this is an EG47. Let's look at all the different material types, profiles, weights, dimensions, and try and optimize those where possible. A lot of this work came from our sleeper strategy working group, which is attended by the environmental team, TA, SCO, and also some of the routes and regions and some of the projects as well. So we've got a good following there, a good stakeholder working group looking at different specifications, looking at the strategy for hardwood, looking at, is there a replacement for steel sleepers, because steel is quite high in terms of CO2, and also some guidance on the best sort of sleeper selection that we can use within our track renewals as well. And that's in terms of performance and also in terms of sort of low carbon as well. Of switching crossings and S&C, we've extended some of that work onto that. These are actual slides that we showed at the PWI S&C seminar we held in July. So this is really looking at the sustainability and circularity of S&C. How can we improve that? These are the questions we asked ourselves just to see, how far do we think we are advancing these? How can we reduce carbon in S&C? Why can't we design, install and maintain S&C that has improved reliability and service life? How can we make better use of our serviceable S&C and some of the materials we have already out there? What technology and equipment is needed to monitor and maintain S&C to increase asset life? And how do we sustain the competence? So sustaining competence is also an important thing for us in terms of making sure we can manage S&C for the future. So for S&C, for the carbon S&C, we broke down the individual parts into the bearers, the rail, the castings. There's still some areas we don't know. We don't know point of operating equipment carbon equivalents. We do for ballast, we do for rail, we do for concrete, because we're doing that for plain line, so we can apply those low carbon concrete mixes for S&C as well. The green rail for S&C and castings, and also there's some work there to be done on recycling ballast. So if we sort of employ or use the low carbon concrete and green rail, we can actually have a reduction there, you see, of 29,000 kilograms of CO2 for a DV switch, which is quite a lot of saving. Most of that saving is within the rail itself, as you can see, some in the ballast, but not too much, and some in the concrete as well. So that's for a typical DVS turnout. So 35 tons of CO2. So really that's equivalent to installing 70 meters of plain line track. So in terms of recycling, we do have a recycling centre at Whitemoor, which is heavily underused. We do source those materials from projects and from the maintenance teams when they're deemed to be serviceable, and they're taken back to Whitemoor and then refurbished and reused. So in terms of rail, so the top section there shows us that we have 93,000 tonnes of scrap metal recycled. So that's equivalent to 13 Eiffel Towers, and the saving there from metal recycling is 7.5 million. At the moment, that metal doesn't go directly back into making rail, but there's work in progress to look at how we can make sure that the scrap rail that we do scrap, we don't sell as scrap, we sell it as rail to our rail manufacturers, and it goes circular. So that's improving the sort of circularity of rail. Ballast, you can see 1.26 million tonnes recycled every year. 156 of that was recycled at Whitemoor, and there are other aggregate handling depots that recycle our ballast. So this is recycling ballast, but at this stage, this isn't going back into track. This is going off for other uses in other infrastructures or other uses outside of the railway. Some of the work we're doing, which you'll see later, is to actually start to recycle ballast so that we can use it within track, as we do with a ballast cleaner. So the recycling centre, some of the benefits we get from that are the reduction in CO2, cost reduction in the purchase price, also the depletion of natural resources, because we're not extracting iron ore, we're not extracting ballast or granite. So we're using, it's already been worked, and we've basically just got to reuse it, make it serviceable, and then try and make it as circular as possible. In some cases, we've got some parts that have better availability in emergency situations for spare components, reduced lead times also. So most cast crossings nowadays can take up to sort of 20 to 30 weeks to order. But with these, we know we've got cast crossings that have been refurbished and we know the sizes and they fit, then we can get them within 2 or 3 weeks. And availability of assets for cascading and renewals and so on. So that's some of the benefits. We're just not seeing the uptake at Whitemoor. Maybe we need to spread that out to all the local regions and routes, and they have their own small recycling centres, and they manage it locally. and then the centre is Whitemore, and they can then manage those areas. So that has been mentioned, and that may be a better way of doing it and managing sort of those assets. So for competencies and making sure we sustain those for the future within S&C, because sustainability isn't just about the environment, it's also sustaining things for the future, and competencies is one of those. So new technology does require competency assessments, before we introduce. There's some embedded learning that we may need to introduce, and we may need to increase sort of the learning capacity, because there may be some new technology that just isn't understood yet. So we need to sort of increase that learning capacity. There is a millennial generation of learners that we need to sort of align our techniques with, to make sure we're not doing reams and reams of books and rule books, and we're introducing and sustaining competencies that can be easily understood and digested. Understanding the learning and training needs. We introduce quite a lot of products for future use, but we don't really understand how we should be training those products as well. So understanding that. That also goes with cross disciplines. So where we have a signals, track and civils interface, making sure all disciplines are aware and they have some form of competence across those disciplines as well. So developing topics that are actual specific learning material that's easy to access and more motivational than just presentations or videos, so maybe some augmented reality, so people can start to sort of get involved and actually use it, albeit digital, but at least they can use the and train in an augmented reality state. So going on to whole life carbon, we've looked at how we can measure whole life carbon in track, and what are the activities, how do we use those activities, what's the effect of the activity, and how can an accurate or average cycle rate be determined. So in terms of how many times do we tamp, how many times do we grind or mill or re-rail or re-key our track, so that we can then sort of determine some values for carbon. Similar thing for costs. So you would look at a cost model, you look at the carbon model in that way. And then you have to sort of make sure that you don't have double counting, that you aren't any gaps. And so making sure you look at what's included within the activity, whether it's the machine, whether it's the transport, whether it's the people to site, whether it's the consumables, and the fuel, and all those things that all tie into that. So for each one of those activities, we've looked at those scenarios and the usage effect. If you sort of put that onto a table, so this is a baseline with 1 kilometre CWR concrete track, Cat 1. So it's a 440. It's based on a 440 yard renewal pro rata, so it's 2.5. So it's creating a 1 kilometre track, and this is using our current maintenance strategy, 30-year service life, and that's without an undersleeper pad. So sort of standard baseline. So along the top, we've got 30 years. We've got the cycle rates in as we go down each one of those activities. So we have one renewal, then there's tamping, grinding, and so on, rail exchange. So we can then create a CO2 figure for that. We can look at the total CO2 figure, and we can also calculate a whole life total there. So in terms of kilograms per metre per year, we've got 31.2 there. So that's our sort of baseline rate. If you were to look at an improved version of that, so that's using lower carbon sleepers, lower carbon rail, also with rail replacement, using lower carbon rail for the rail replacement, recycled pads. Other things that we've introduced as part of this as well are an extended life. So you can see that's now 50 years, because we're using better materials, higher performing materials, autonomous inspections instead of basic visual patrolling inspections, and also some battery locos or EV locos for sort of delivery of the track renewal as well. So that's actually giving us a kilogram per metre per year of 10.7.2, which I think equates to a reduction of 66%. So that's quite a large reduction if we sort of start to, and that's employing technology that's available today, and some of it is still work to be done, but it's not far off. So that could be the norm in, say, 5 or 10 years time. So looking at that model and looking at what we can do for the future, we decided to initiate a first-in-class low-carbon track demonstrator. So the mission really is to complete a demonstrator project showcasing all our lowest CO2 emission available. So for track renewal, so it includes the embodied carbon and all the transportation for all those components that I mentioned earlier. Also construction and site welfare, site activities, transportation in the plant as well. So it's using all the current approved materials or items that are actually suitable for trialing, so that we can show extended life and reduce carbon as well. And it's bringing those together. It's basically testing them, using them, and then making them become business as usual. Because some of these are starting to become business as usual already, and if we don't shout now, people just won't realise the work we've done. So it's almost a case of, this is what we're doing, this is going to be business as usual, but there's still work to do, in some areas. So breaking it down, we've got green steel, Sen 60 rail, there's a 64% reduction in carbon there. The Sem 2 concrete, which is the new G44 from Cemex, 40 to 50% reduction on that, on those sleepers. Recycled ballast, 25 to 50% reduction. It's a small reduction, but nonetheless, it's still helping us reduce. Recycled pads and clips, quite a small percentage in terms of the overall, but we're looking at around a 40 to 50% reduction there as well. So the total reduction in track construction using these recycled materials or greener materials is around 50 to 55%. If we start to use undersleeper pads as well, we can see a sort of whole life CO2 reduction as well by extending the life. And currently they're not mandated for use. There is a small cost increase, but we know that cost increases has huge benefits in terms of whole life CO2 and whole life cost. Over the next 3 years, so looking back at 2022, we baselined sleepers in terms of the CO2 per sleepers. We looked at each sleeper type, so timber, steel, concrete, composite. We actually purchase over 500,000 sleepers a year. So looking at 2022 to 2025 and how we can phasing out hardwood for composite sleepers, reducing the steel rate from 150 to 75, and concrete from 105 kilos to 65 kilos, and also composites, an increasing use of composites due to hardwoods reducing, but there's still, the amount of CO2 in a composite sleeper is 38 kilos, so it's one of our sort of lowest or greenest sleepers we have at the moment. So these are all volumes based on sort of previous purchase and some of our sort of CP7 and plan rates. And so we look at the forecast rates as well to make sure we've got the right data for this. And it's also showing that the phasing out of hardwood for composite as well, which shows that carbon reduction. So again, we're looking at that figure, it's 50% overall reduction, and that's just looking at the sleepers, and that work is in plan. We're already there with the concrete. Steel is probably debatable. We need our supplier there to push this and make sure we get green steel. And the timber to composite has started, the phasing out has started as of this week. So we know we're somewhere to meeting those targets already. In total tracked CO2 terms, 22 baseline versus a 24 baseline. So this is only 2 years time. And that's really, we've chosen that because it aligns with our first-in-class track trials next year. So again, using electric arc furnace rails, low carbon G44 sleepers and recycled ballast, they're the savings we can get there, showing the breakdown. So this really shows you the sums for the CO2 for a sleeper, for a rail, for the ballast and so on, and shows the full volumes. And that reduction is from 440,000 kilograms down to 204,000 kilograms. So, and that's for a typical kilometre of track as well. So yeah, that's another good saving. So around, like we said, around that 50 to 55% reduction. The smalls, the pads, the clips, the nylons, again, they're all up for grabs in terms of recycling. We've asked our suppliers to look at recycling rail pads, so Tyflex are looking at that. Pandro are looking at the rail insulators. So it does rely on a feedstock, so we have to give the old pads and nylons back, and then they can start reusing them and mixing them, and they can look at the percentage of what you call feedstock, which is the old recycled material versus the virgin stock that then goes into it, to see how much carbon they need, or how much new virgin material they need to make it and perform correctly. You know? So again, big savings there as well, because we do use a lot of clips, pads, and nylons a year. Recycling of ballast. So this is creating a circular economy for ballast. So at track removal stage, we will take out the old ballast. That will go back to an aggregate handling depot, which is that bottom right-hand corner there, which is set up in Stoke at the moment by Land Recovery. And they will then sieve, wash, and recycle the ballast to a specification very similar to the new track ballast. We have two specifications for ballast, one for new ballast and one for high output or ballast clean ballast as well. So we're looking at the two standards and specifications and making sure we get the right specification for recycling of ballast. So ballast isn't actually a high CO2 product or material. It's only 7.5 kilos per ton. It's really low. So it's actually one of the lowest sort of embodied carbon materials we have in track. So this is more about the saving of natural or depletion of natural resources. So the granite that we quarry, and basically leaving a scar in our countryside. So it's reducing that. There is a small cost saving. It's not huge, but we can hopefully reduce the 7.5 kilograms per ton down to around 4 kilos per ton as well. And the real aim here is for future. So you won't be purchasing recycled. You won't be purchasing new ballast. It will be a mix, and the mix will be something. It could be 50-50, 60-40, 40-60. There'll be a pure mix of new versus and recycled. So you won't be specifically buying just new. And that's how we can introduce it. We then don't introduce, two different products, and people don't have to choose which one they want. So within supply chain operations, we'll basically say, this is the ballast we are now providing you. Again, it's reducing carbon, improving circularity. So what we need to do as part of this is to look at, what effect recycled ballast has on the track. So some of the benefits are, so currently we show that 60 to 80% of spent ballast can be recycled. So that gives us a figure of how much we can actually recycle. In terms of this, we think it'd be around more like 70% that we can reuse. So that's washed, sieved, and loaded back into wagons. So depletion of natural resources. So that's 1 million tons per year we currently quarry. 50% reduction in CO2. And the washed ballast is actually reducing the ballast dust particles and the fines. So we know there's sort of safety concerns over the amount of ballast dust we get. The actual, once it goes through this process, we have cleaner ballast. So it does remove all those fine dust particles. Some of the outputs can be used for sand and for sand blankets. So we do get sand as another output from recycling. And also we're looking at using the aggregates, some of the smaller aggregates within sleeper manufacturing. So we can have recycled aggregates within sleepers, and also pathway infill. So there's quite a lot of other work there we can do. So we're saying a 50%, and it's based on our current environmental product declarations, and that does need to be validated as well. And when we have a product that's more accurate, we know we can then put it through the EPD process and calculate that. And we're not far off that at the moment. So the proposal, it's going to be a mixture of recycled and new, and it's for bottom ballast and top ballast. So it's all for all track. And also for dressing and topping up as well, for tamping and so on. And some of our timelines here are approval for the ballast blend by April 24. That could be a test site approval, so we can start to use it. We're hoping we actually beat that date. Full approval, end of 24, aiming for. Sponsors, we've got Eastern, Southern Rail System Alliance, Wales and Western, Technical Authority, and Supply Chain Operations. Supply Chain Operations are actually funding a lot of the testing for the recycled ballast. The working groups, so this forms part of the sort of track TA environmental working group, sustainability working group, and asset leadership and discipline leadership groups as well. So to understand some of the risks and the disbenefits of recycled ballast, to enable us to see where we need to test and gain evidence. So we looked at what could go wrong with recycled ballast, what are our concerns. So listing on the right hand side, the variability of quality, consistency of granular material, impurities from excavation materials, how we make sure we remove those, loss of angularity. So there's three things you expect from ballast, and that's angularity, the roughness, and the shape. They're the three things that make ballast perform. So understanding how the reduction in angularity can improve or be just as good as a angular new piece requires some testing to make sure ballast does lock, ballast doesn't move, and it consolidates in the same way that new ballast does. There's a lot of testing we've been doing on that to sort of prove those theories and principles. That's with University of Southampton. We're doing sleeper lateral resistance tests with sleepers using recycled and using new ballast and using mixes thereof as well. So we're also looking at the change of particle shape, how the ovality changes in the shape. What we have found is those rocks that do survive from recycling through the recycling process tend to be the stronger rocks. So we know we've worked it, and it's the stronger rock that still exists in its sort of larger shape, whereas the smaller ones have broken down. So we're seeing that the larger ones and the stronger ones are surviving, and yes, they're becoming slightly rougher, but they're still compacting to a good rate and a dense rate, and they're also managing the track stability and lateral and vertical geometry of the track as well. Ballast migration, so if we've got ballast that's more rounded, that then tends to sort of move around and shuffle around more and under load dynamically, then that'll be a concern. The reduced strength in terms of vertical and lateral forces we exert on the ballast. Lateral stability, as I said, so looking at the testing for that as well. And how much organic content can vary as well between when we dig out and when we install recycled ballast as well. Is there a certain amount of organic content that's allowable within this? So all of these are actually going to be evidenced within the product acceptance to prove that recycled ballast meets the requirements of sort of new track ballast. So that's part of our test criteria. And this is part of our plan, or what we're going to do. So to gain a trial PA certificate, we've already got some testing done. We've done some lateral strength tests with sleeper lateral resistance, and we've actually proven that the recycled ballast is just as good as new ballast on lateral resistance and also on compaction. So those results have only just been reported. But they're all very positive, very positive in that sense. We're doing some triaxial tests, so we're doing some dynamic triaxial tests to see how much movement we get within that, and to see if any of those particles do crush and break down as well. So we're doing that with various different mixes. Some in-field monitoring, so we're going to do some sites with recycled ballast, and then we're going to monitor the sites. So that's 2 or 3 trial sites selected on the Anglia region. Vertical settlement, we've looked at some compaction versus displacement rates already, and they're very positive. We're going to do some more tests just to make sure we haven't missed anything, to make sure that the compaction rates of recycled is just as good as new. And also some independent quality auditing as well, and sort of the associated documentation that may need to come along with this. Some of that may be a new standard or a change to a standard. But we're also looking at sort of the petrochemical and petrograph analysis as well to make sure the actual rocks themselves are as or similar to the new ones, what we get when we quarry. They're the standards: 2102, 8100, 009, and there's an EN standard also that we're looking at. So we do have within for circular economy, there are some areas that we need to I guess address, certainly in terms of green rail feedstock. So that's making sure we have the feedstock for recycled rails. So scrap rail supply is limited. It's the long welded train that we only have availability or small availability of, and picking up from site and then transferring that to the manufacturers to be sent to the supplier. This one particular where we're getting our green steel from will be France, but eventually that will be the UK, but that's the France is just for the trial. Recycled ballast stockpiling logistics, making sure we have that across the country. Currently it's only in Stoke-on-Trent, but we then need to duplicate those in all of the other aggregate handling depots as well. Unit rate costs, so CP7 unit rate cost for track renewals is pretty fixed. So if we do have some variation in some material costs, we need to understand the cost impact of that. Green steel is 20 to 25% more expensive. Recycled ballast is 50% more expensive. However, that's because the price is about to go up by 60 or 70%. So some of these are fixed, or some of these are actually about to happen, whilst there's also a price increase about to happen on the normal material. So we need to balance that out as well. And unit rates for track renewals also are not really aligned to change with the unit rates of track materials as well. So we need to make sure we improve that as well. Another, I guess, limitation is the contract durations we have and how we extend contracts with an SCO, making sure, you know, any change of material type that takes place within contracts can be amended or renewed within a certain time frame, so it hits certain deadlines and targets, so it could be CP7 or CP8. So it's looking at when that may happen. Another item that's I guess on the circularity part of sustainability is this is the timeline for phasing out of hardwood to composite. Some of you may have seen a bulletin that went out earlier in the week to basically state that SCO will no longer be procuring tropical hardwood sleepers as from May 24. So this is our timeline. So it was a paper we sent to the executive leadership team where Andrew Haynes approved the phasing out. And then we put in place this timeline to deliver bulletins, also gain full approval for a high-speed equivalent composite sleeper, and also to state where the other contracts with track work and so on will need to phase out. And this is for hardwood sleepers, not for S&C bearers. So if S&C bearers are hardwood S&C bearers will still be purchased. This is just more for sleepers. So that's we've just shown the timeline of where we need to get to for that. So that's quite a big win for us in terms of the environmental improvements that that brings. So a lot of the products we do produce, a lot of people say, well, are they approved? Are they business as usual? Can we get them now? So we put together this table just to show people where we are. So first item there is the G44 and EG47. So that's a trackwork mold product. Cemex also do the same thing. And we've got a new low carbon mix, and they were approved earlier this year, May and June. That's reducing the carbon between 40 to 50%, 30 to 40%. So that for us was a big win. The Sycot composite sleepers, again, reminding people that they've been approved since February 23 for issue 2, and that we're also have trial product acceptance or product approval for March, that started in March 23 for 110 mile/hour sites, and also for use on adjustment switches. Sekisui 160 mil FFU, so that's the FFU Sekisui sleeper bearer, the bearer that we used at Newark. That's also approved for trial on ballasted bridges up to 125 miles an hour. So that at the moment is our sort of forefront high-speed composite sleeper that we could use. That's going to be gaining approval prior to the hardwood composite sort of phase out. Recycled ballast. So we know it does conform to TRK 009. It's making sure we can make it conform to the other standards, and also getting the PA for that. So that PA is underway. Recycled ballast undergoing assessment. Nothing started, but we hope to start something in 2024. Getzner high lateral resistance under sleeper pads. So no trial PA at present. We're doing some lateral resistance testing. So this is a new USP that's hopefully going to increase the lateral resistance of a concrete sleeper to something similar to a lateral end resistant plate. So hopefully it can reduce us putting in LERPs for the future. Part of the testing we did with Southampton is looking at what do LERPs actually add to the mix for lateral resistance, and how that aligns with mod 14, CRT, critical rail temperatures, and resistance of track buckling, and so on. So a lot of that work sort of stems into that. And then there's the SAR style Sen 60 green steel rail as well. So it's approved, all approved for use in November 21. We've just never purchased it, and we don't have a contract to purchase. So we're putting in an STA, a single tender agreement, to purchase a small amount to do the trials. So that's the status for those products. In terms of sleepers, we do get queries about what's the best sleeper for the best track usage type, what's the best lateral resistance, what has the best lateral resistance. So what we decided to do was to do a life cycle assessment criteria, and this is our existing sleeper range. We've got one for the newer sleepers we're looking at as well, but this is just what's currently available for us that's approved. We've got whole life cost, we've got the average tonnage per year that you would see for those sleepers. We've got the average tonnage over a lifetime. So that's sort of creating a functional unit that we can use to show that we can actually get a certain tonnage over a lifetime. What the main track category usage types are for those sleepers. Lateral resistance, so high meaning good, a good lateral resistance, down to low where you've got your hardwood, which is very low, hence why we have a CRT value for that. Ballast and geometry degradation rate. So, certain sleeper types work well with ballast. Certainly with under sleeper pads, you've got a low degradation rate. You're not breaking the ballast down into the smaller particles, and you're retaining your geometry by doing that as well. So USPs give you that lower degradation rate, and composite sleepers also do the similar thing because they're not so hard and stiff, and they don't break down the ballast as much as well. And also you're looking at the way the geometry is retained, so it's not just about the ballast, it's the geometry retention in all senses. Stiffness and strength, durability, and we had to add fire and safety performance. Though concrete, you're never really concerned about the fire safety, but introducing new plastic products such as recycled HDPE and FFU and all these other new composite materials we're using, we've had to look at it from a sort of fire and safety perspective. And that safety perspective could also be tripping. It could be, are we introducing a surface that when we walk on it's more prone to tripping and slipping? And also that the content in terms of fire flammability, smoke, so the density of the smoke, the toxicity of the smoke as well, when we're in a sort of an enclosed environment, so say tunnels or anything where the sleeper's on fire, or lots of sleepers are on fire. And also the flammability. So it could be the flame spread from one sleeper to another. If a sleeper sets fire and it just suddenly radiates that heat onto another sleeper, and then you have a chain reaction and all your track is on fire. So these are new I guess areas we've understood and learned about over the last couple of years, and speaking with the fire engineers to understand that risk as well, and making sure we're doing the right thing. And in terms of the worst material to put in a tunnel is wood, because it's so flammable, and then you've got plastic, and then concrete is obviously the best. And on the right hand side, we've got the sort of CO2 kilograms per sleeper as well. And that range is because different suppliers have different rates of CO2 depending on their manufacturing facility and methodology and so on. So Cemex would have a really low rate because they're using a carousel method, which doesn't use a very large space and doesn't use a lot of materials, a lot of water and a lot of heat, and there's other things to go with it. So there's a big saving there as well. Just some, I guess it's summarized guidance really in terms of for designers, certainly when they're looking at excavation, sleepers and ballast, and what savings can you get in terms of designs. So if we were to look at reducing the excavation depth from 300 mil to 250 mil, there's not a big saving. It's only 6% of the total tracked CO2. So, you know, is it worth us doing that? This is some of the questions that we were asking. You know, can we reduce ballast? Yes, there's a cost saving, there's a time saving, there's a train space saving as well. But in terms of carbon, it's not big. Installing LERPs add an actual additional 4% of CO2 to the track renewal. So can we reduce that? And that's to every other sleeper, so 8% if we start to put it on. So adding a LERP to a renewal is not only cost, but also more carbon. So can we reduce that? Can we think of ways of not using LERPs, or change the standards, or understand where, and more precisely where we need to use LERPs rather than try and blanket it or have a safety factor in there. Using recycled composites in place of timber, so that's an 18% saving. Using recycled ballast can save up to 2.5%. We now think that's around more than 5, but we said 2.5 just to be safer. Track standard 2102. So this is the design and construction of track, and it specifies these requirements, but material choice will really default to sort of low carbon track materials in the future. So we're trying to make, you know, that choice. So rather than people having a choice for certain types of sleeper, if there was no choice and it defaulted to the lowest sort of carbon track, and the and what we deem to be the best performing sleeper, then, you know, that's better than having a whole range of sleepers that people can choose from. And using under-sleeper pads can extend ballast life and track life by 20%, and therefore whole life carbon and cost savings can be made. So yeah, they're all some of the things that we're trying to install. So there's no hard and fast guidance for designers, but there's some of the sort of the headlines to sort of make people think, okay, right, if I do this and do that. And the RSSB carbon tool does allow you to sort of, you know, to adjust things and look at things, and it's going to get better when they have the newer materials in there as well, the newer carbon rates from our new sleepers, which is due to be updated soon. So, and I believe that is the end of the presentation. So let's open up to questions.
Thank you, Darren. That was for giving us that excellent talk. I think this topic's very relevant to the rail's current situation at the moment with trying to reduce CO2 and, you know, looking at how alternative methods and materials are selected and being currently used to help to achieve this. So thank you for running through that. We've got a couple of questions that have been put in the chat. Is there anyone who wants to ask a question? Just want to raise their hands to kickstart us off. Otherwise, I will go straight to the chat. Okay, let's start off the first one, which is from Peter. And Peter's asking, where signalling cables need to pass under a track, would this still mean metal hollow bearers, or would there be a composite alternative?
Good question, Peter. So there are obviously concrete cable management sleepers that we use, the wider ducted ones that you could put the larger power cables through, and those concrete sleepers are becoming greener. So they're, in terms of performance, we'd want to use the concrete because they are stronger and stiffer, certainly for passing cables through. So that's EG 55 and EG 47s, I think they are. No, sorry, EF 47s and G 55s. So we've got concrete sleepers that do that. For composites, the composite manufacturers are looking at it. They're looking at routed. They're looking at small cables can be cleated on anyway, but they're actually looking at how they can groove out or bell mouth to create something similar to concrete with the two fastenings each side. Not developed yet. We've seen some really early sort of innovative solutions, but we'd be concerned that the strength just isn't there. So some composite materials lend themselves to being made into a hollow frame. I've seen a GRP hollow sleeper has come to us as well to look at, but concerns there that they haven't really tested it. So they are looking at it, but not available on the market at the moment. But lower carbon concrete is being explored, and that's something in the next 6 to 12 months that will be available.
Thank you.
Okay, thanks for that. Next question is from exactly right. So he said, great presentation, Darren, very informative and inspiring. So he's got a couple of questions. So the first one, USP will erode over time and can become microplastics flowing through the drainage to natural resources. Is there a measure to manage the toxicity for the USP?
So this came up not just for undersleeper pads, but it also came up for plastic sleepers. So anything that's abrading, eroding in the ballast, those particles go into the watercourse, and there's a leachate rate so we asked the question to our environmental team: what's an acceptable microplastic level that if we exceed it is going to be a concern for for toxicity? And there was no figure given. But what we have in the standard is we asked them to do an abrasion test, and for those particles that do, and that's in a ballast box, and those particles that do wear off, we look at how much that is, and we've got that figure. And there is a certain percentage of, I think it's 2% or 1.5% of the overall mass can't degrade down into those smaller particles and go into the course. But we actually put the question to the environmental team saying, can you give us a figure? What's acceptable? Obviously 0 is what we want. We don't want to put anything into the course. And USP rubber is different to plastic, so microplastic. So we do have a microplastic clause within our standard that says we don't want microplastics wearing off and going into the ballast. But what we don't know is what is acceptable and what's not acceptable, because that's not been determined. So parts per million, we said, is there a parts per million you could but then I think people said they found it difficult to be able to calculate. But it's a question that's been raised, but no one in our environmental team has been able to give us the actual that I guess acceptable rate. And concrete sleepers, so over designed, yes they are. So there is a concrete sleeper working group. We know that we are over designing sleepers. If you look at the EN 13230 and you look at what we do in 030, we're about the order of 1.3 above what they do in the rest of Europe, and compared to sleepers in Europe, our sleepers are far more superior. And a lot of suppliers say, why are you making them that strong? And I guess the answer is no one wants to go back now. No one wants to make them less strong than they are now, unless we can absolutely prove that it's still fit for purpose. Or maybe we do it against a set tonnage. So why do we need a G44 for areas where we've got low axle weights, or a very low, say cat 3, 2 million tons per year or something like that? Why can't we have smaller sleepers or different sleepers for that? And there is some saving there. You could have a low use sleeper and a high category sleeper for cat 1, cat 2 in terms of concrete, and you could save quite a bit. You could probably save about £5 to £6 a sleeper if you went down that route. And the concrete sleeper strategy and the sleeper strategy working group are looking at all of these things, where we can change standards, where we can improve specifications to get better products. And there is a new sleeper specification that's being developed, being drafted, that covers this as well. So it covers low carbon, circular, it covers also toxicity as well, is mentioned in there, and also the strength. So going back to first principles for strength of sleepers, rather than looking at what it says for the rates that are in 030. So there is work involved in that. I hope that answers your question.
Okay, got a couple more questions. So one for Peter. How much would using axle counters rather than track circuits for train detection help in not requiring installations insulated rail joints, etc. Would there be any change in need for pads and nylons, or are these needed independently from mechanical considerations?
That's a good question. Yeah. So there's probably quite a lot of assets, signalling assets, that I'm not sure in the signalling world they've got to that stage. They've looked at those individual assets to say how much. So that comparison between axle counters and track circuited, I don't think anyone's ever done that. But I would say, I guess there's the cabling, there's the joints that have got to be maintained. It's more a maintenance type of thing. So IRJ, insulated rail joints, do take a lot of maintenance, and maintenance is carbon because people are going out and they're spending a lot of time and a lot of effort to pack up a joint. So axle counters for me win. And then there's the cables that you have to sort of deal with both really. But in terms of ensuring you have, I guess, you have that correct insulation between the two rails, you still need pads and nylons to obtain the correct toe load for a clip. So you still need a pad because that also has the resilience in there, so it stops the concrete sleeper from basically the impact loads and the vibration going to the concrete and the concrete. So we still use that to absorb the vibration and loads from the wheels. So that's still there. Insulators also provide a mechanical, and you say it is mechanical, between the shoulder of the sleeper and the rail foot. So it stops the two metals rubbing and wearing away. So insulators, whilst provide insulation, they also provide that mechanical barrier between the two to stop them from eroding, and some form of resilience there as well. So you've got some resilience, and combined they set the clip height, so the pad sets clip height, and the insulator also does the same thing if you're working on the insulator to make sure you get the right toe load as well. So we do still need them, unfortunately.
Okay, so Peter, who asked that question, has just put his hand up. Did you want to dive in, Peter?
Can I ask a supplementary? Yes, I rather assumed that they were there mechanically as well, but I'm also wondering that if they begin to fail, a track circuit is, the track circuit's down, you've got to go and fix it now. If it's only, inverted commas, there for mechanical things, you might be able to live with it for a long time. You might not even know it's failed. So that is one element of it. Does it reduce help in that way? But also, if I think, for all sorts of other reasons, we're more likely to go to axle counters than track circuits. But if we were doing, the signalling department, for want of a better word, was doing an evaluation of the reduction in the carbon or whatever, whether we would, as a signal department, be considering the effect on the track. We might be comparing our track circuit from our department's point of view with an axle counter. But if it did make any difference to you not requiring insulated rail joints, and there was a carbon impact on that, who gets the credit? I.e., we don't want to double count it, but we don't want to miscount it completely, ignore it. Where's the demarcation line?
Yeah, so I think the two disciplines, track and signals, need to work together on that. And you're absolutely right. So you look at failure modes, and you look at, so if you do drop a track circuit because the insulation's dropped, fine. But if you don't rely on that, like you do with axle counters, then that's one failure gone, isn't it? So there's a tick in the box there. So if it's more okay, if you're looking at the carbon saving, cost saving, reliability saving, and all those things, that they all add up to carbon. Someone just needs to do it, and I guess someone's probably, in terms of track circuited versus axle counted. I don't see many areas where they're saying, actually, this is a new system, let's put track circuits back in. So yeah, I guess I don't know how rigorous, how those standards are actually applied, and are signal standards aligned to carbon? I don't know. I don't think they are at the moment. Whereas
they're not. I don't think they're aligned to carbon from that point of view.
Yeah.
As far as axle counters are concerned, yes, you're dead right. Unless there's some very peculiar situations, we would generally now, on a new job, put in axle counters. However, just like PWI equipment, whether it is worth going to replace existing track circuits by active counters. We sometimes do in reliability points of view. We certainly have a lot on the Great Western Main Line, but whether the cost benefit of doing all that is worth it or not, if there was a significant carbon impact, you would use that as a part of the business case for doing a premature change, if you like to look at it.
Absolutely, you could. It's like point machine overhaul. It's like anything that, you know, OHLE and all those, I guess, changes or improvements in those asset areas. But it just needs that sponsor from. The problem with track renewals is track renewals are maintained by a track sponsor, not a track and signal sponsor. So if you want to, at the same time as doing a piece of track and upgrade the signal equipment as well, you need funding from track and signals in the same pot. And route engineers can do that, you know, but it becomes quite difficult, you know, to strategize in that sense and to align track and signal strategies. But yeah, and so you're quite right. Your statement is we should start thinking about the carbon savings and improvements, not just the cost saving. So when we do cost impact analysis, why aren't we doing carbon impact analysis? Because we're not, you know, we're just still doing, you know, and soon we'll be charged on carbon. There'll be a carbon tax rate, and that carbon tax rate will have to then feed back into our unit rate costs and go, oh, the carbon tax rate is £2.5 per kilogram, you know, and we've just spent, you know, so and that's going to affect us in the future. So we're going to have to start thinking now about to make sure when that does come in, we're not just suddenly hit by, you know, a huge cost. But yes, good point.
Thank you.
Good point, Peter. And I see note from Sapter to talk about FFU. Yep. I've been involved with lots of FFU, S&C installations and so on. It's more when you burn FFU, the smoke toxicity of the smoke given off, because if you know what's in FFU, you'd understand why. When you burn urethane, it's not good. So it's that's what needs to be tested. So we have to look at toxicities. Flame spread isn't much of an issue. With fiber foam reinforced products, but it's more the toxicity and the smoke density as well. Certainly when you're in a tunnel, when you get a large, you can't see where you're walking is one of the biggest issues. And London Underground have found that out via various incidences. So
he's popped his hand up. Did you want to dive in there?
Right. Yeah, right. Perhaps maybe I just want to ask some supplement question from the previous one. Also, FFU, for example, for FFU, it won't be burned. It means that the toxicity from the toxic is really low because there's no smoke out of it. The fire will be extinguished by itself. So perhaps maybe you could try. It's different to different other type of composite that use a lot of resin, polymer resin. So we have to distinguish them separately, that they have different characteristic for FFU. But let's back to first. I'm wondering, you mentioned about USP that 2%. Is that 2% come from construction or from the whole life cycle for erosions of the material?
That's the whole sleeper in the ballast. So it's as it's being tested. If we have 2% loss of weight, so this is something that was introduced
for the like 50 years of the service life.
Yeah, what you could argue that. So the 3 million cycles for ballast test isn't really.
I know. That's what I was trying to ask, because when I see the report, I think I have seen the similar report, and they think that hang on, and they claim that this is the whole life. I said hang on, but it's only the standardized test.
Absolutely,
it's not whole life cycle here.
It's accelerated.
So I don't blame you. I just said that I think we have to be precautioned about the result that they put to us. And the second question is that for the sleepers, concrete sleepers, it's not about just cost, but I do remember from last time we did some analysis at Birmingham University, we found that current design standard produce around 20% more material usage. And it means that we use more cement, we use more of material, and we create the waste within the component. So there is a reason why I'm not talking about the cost too much, but I'm thinking about material because for example, you order 500,000 sleepers a year.
Yeah.
Imagine how much material that has been waste throughout the drain. So this is just a question. I don't blame you, but it's just a system issue that we probably have to tackle together, I guess.
And you're absolutely right, because that reduction in the amount of concrete we use for a sleeper, because we are making it too big, too wide. So we've already said to our suppliers, can you make a more slender sleeper, a thinner sleeper, but still have and with the strength properties, tell us what you can get, and then we can challenge what we actually have in our standard, but also compare against what you do for Germany, France as well within the EN standards, and then we can see where we can get to. So we've looked at the amount of savings we can introduce, in terms of volume of concrete. So going from 309 kilos or for a G44 down to 242, I think, or something like that. So it's quite a big savings, around 20% saving. And that can save us another 8.5 kilos by changing the volume of concrete we use as well. And we're looking at green steel. So green steel for the reinforcing and recycled aggregates, all sorts of different new mixes. CEM 3 is about to come in as well. So we can get a concrete sleeper down to 50 kilos now using one of our methods. So when you think 2 years ago, it was around 100. So it's got a lot better.
Thank you very much. Thank you.
Okay.
Okay, we'll just finish off quick with this last one and then we'll wrap it up. Appreciate we've gone over slightly, but the last one, just from Matthew, just saying hi, thanks for the presentation. Presumably for the composite sleepers, a large portion of the carbon would be in the steel base plate. Are you looking at alternative fastening arrangements for composite sleepers?
Good question, Matthew. And absolutely right. The base plate itself, I think, says 33. There's around let's just try and think, about around 20 kilos or 18 kilos is within the base plates. So there is a project. I initiated it. It's now gone into another phase, and it's looking at integrated fastenings within composite sleepers. So basically, at the moment, when composite sleepers were first procured and approved, it was to replace timber. For timber, we just fix a base plate to it with screws. So they wanted that functionality. We've ticked that. That's good. We can put all our different base plate types on. Now people want something that looks similar to a concrete sleeper with the shoulders and housings integrated and molded into the casting. So the project that is ongoing at the moment is to look at a new plastic molded sleeper that has a very strange shape and profile, which digs into the ballast and gives you that high lateral resistance, but it's also got an integrated fast clip housing. So you cut the CO2 down, and we can get the CO2 down to around I think 18. The only problem with that is the housings got slightly bigger because they need some other form of sort of strengthening underneath it, and certain designs have steel rods in them, and some do. Some have steel rods. Some manufacturers of composite materials have steel rods, and some don't. So then we've got to look at that sort of, that balance. But yeah, that started, Matthew. So in a year's time, we'll be trialing those new sleepers as well. So Southern Rail System Alliance are helping with that. And the TA are sort of managing it as well. So brilliant. I think that's about it. We got all of the
Excellent. Yeah, we've got a lot of questions this time, but thanks again, Darren, from the Birmingham committee. I think that was a very interesting talk, and I think that's evidenced by the amount of questions asked for you. But yeah, we'll wrap it up there, and for everyone in the Birmingham committee, hopefully see you in our next event. Look out on the website when that's available, and it should be sometime November. Okay, thank you all, and take care.
Thank you, Kate.
Brilliant. Thank you.
Tony.
Bye-bye.
Cheers, everyone.
Yeah, thank you.
Thanks all.
Thank you.